Okay, so we have now a keynote, and I'm really proud to see him again. It's Lionel. There was he has a history in EuroSPI, actually, because when I did my research, when I was still at the university at the beginning of the 90s and in the middle of the 90s, and we formed this kind of initiative in parallel to the Technical University of Graz, I met him, and he was a contributor to the first conferences. Yeah, so he was contributing to, at this time it was called ESI-ISEM, because at this time we had still a European Software Institute, and this conference here was originally thought as the main conference to collect people around that institute, but we decided differently later. Yeah. And at this time he was a speaker, yeah, and he was co-writer of a book. He helped us a lot to found the thing, and then he vanished for 17 years for me. Okay? And this year he arrived again. Right? So, Lionel, I met him as a very, in the 90s, as a very active Canadian, yeah? Really being in this time one of the leaders for software measurement issues in this area where we worked and where he contributed to our conference at this time in this week. Yeah? And now I'm happy that he has returned back. Yeah? So I met him now again because he was proposed as professor of University of Luxembourg, and he's again overlapping with us, especially in cases where we deal with problems in our industry. We have here automotive industry, I've seen we have aerospace industry, we have medical industry in the room. Yeah? And we all have the problem of automated testing, and we have the problem of safe design. Yeah? We had a workshop about safety yesterday, functional safety. So exactly the topics he's talking about now, again, fit 17 years later perfectly into the now actual content of the conference. So I'm happy to announce that Lionel is back. Yeah? So can I ask you to hold your keynote?
Thank you.
Yeah.
Thank you. So, well, good morning. Of course, I would like to start by thanking Beatrix and Eric Dubois and Richard for their kind invitation. I'm very glad to be here, and welcome to Luxembourg once again. I also would like to reassure Richard right away that I've been doing something for the last 17 years. And actually, you'll find out about some of the stuff I've been doing in this presentation. I've also lived in 4 more countries since then, so Luxembourg is the latest addition to my list. So today, I'm going to tell you about something that's quite different from what you're probably used to. It's basically test automation and how to do it properly and how to integrate it into the software development process. So before I do that, let me just give you tell you about the objectives of the presentation. This is not going to be an academic presentation. I'm going to try to summarize 20 years of experience on a particular topic. And what I'm going to tell you is that there are 2 different fields, technical fields. One is test automation, the other one is model-driven engineering. And I'm going to tell you how those 2 can be combined to solve the test automation problem. What I'm going to tell you, of course, is not a silver bullet. I'm not going to claim that this is the right solution in every circumstance, in every context. But in my experience, it works in most contexts, and that's what I'm going to try to convince you about. And last, my objective is going to give you, some guidelines, some lessons learned on how to make it work in practice. And I'm going to do that based on concrete projects. I've been involved in 20 projects over the last years on that topic, and I'm going to show you 4 project examples that are actually taking place in Luxembourg, on which we are currently working, so that I can then draw lessons learned based on concrete examples. But before I do that, let me just quickly tell you the context in which those projects are taking place. We are a center, the center focusing on ICT, security, reliability, and trust. We now are about 220 scientists. We work with more than 20 industry partners. Some are Luxembourgish companies, others are international companies located in Luxembourg. My lab has about 25 people and focuses on software verification and validation. We were established in January 2012 when I moved to Luxembourg from Canada and Norway. Basically, I'm currently working with 6 partners on anything that is related to requirements engineering and quality assurance, test automation, runtime monitoring and verification, security aspects and security testing, and security static analysis of source code. So this is the type of stuff we do. But today I will only tell you about one activity, which is test automation based on models of the system. I'll tell you that in a minute. And the way we work is actually quite similar to Tudor, is that we do research, but we try to do research in context. We don't want to do research in a vacuum. We believe that, in engineering discipline, research has to be driven by innovation needs. And the only way you can find out what innovation needs and concrete problems is by working in a real context. And this is the basis for our partnership program with industry. So that our research takes place in a concrete innovation and development context. Whether we do basic research or we do applied research, there is no difference. The only difference is the timeline and the level of risk. And the way we concretely collaborate in practice, we follow a certain process where we define problems in collaboration with our partners. We decompose and reformulate the problems in scientific terms so that also we can tackle large problems in a stepwise manner. We identify the gaps in the state of the art, and those gaps become our research problems. And then we go through a number of steps which involve, of course, doing the research itself, doing some initial artificial validation that is low cost and low risk before moving on to more realistic validation in pilot projects with our partners. And this is basically our goal, is to have access to artifacts that enable realistic and rigorous validation, the definition of well-defined problems in context, and long-term collaborations. Anyway, so now let me get to the beef of the presentation. And before I do that, in order to make sure we understand each other, I will introduce a number of basic concepts and terminology in order for you to understand the rest of the presentation. I'm going to move that way. So, first testing. I told you, the scope, and we was going to talk about testing. Well, testing is defined as executing software with the intent of finding and correcting defects. Of course, there are many different kinds of testing. First, you have testing before deployment. That can be unit testing, integration testing, system testing, acceptance testing. You all have heard of that. But there is also testing after deployment. Something that people are not always aware of because the technology is not as mature and there is no standard. That is, we all know that no matter how much testing you do when you deploy a system, it's buggy. We know that. So what you would like ideally is, while the system is in use, keep monitoring and verifying it. And at least make sure that nothing silly or worse happens while the system is in use. And that's what I call testing after deployment. Other terms are runtime monitoring and verification, or testing use. Those are the terms you commonly find. And I will mostly focus on the first type of testing, but I will show you an example of the second kind as well. Okay? Because this is important, even though less known and less mature technology. So we all know that there are international standards for testing. This is a standard that was finalized in 2013, an ISO IEEE IEC standard. And what that standard does, it basically defines a number of basic concepts. It tells you about the possible tasks and activities in the testing process, what should be the input and output, the artifacts, what is being produced by each task. It tells you what kind of testing techniques you could use, for example, for test design and implementation, boundary value analysis, equivalent class partitioning, many other techniques that are listed. But there is one thing the standard doesn't do. It doesn't tell you how to automate testing. And we all know that processes are good and nice, but if you cannot afford to actually run a process, well, you're going to take shortcuts. And the problem is that manual testing is just too expensive. So you can have, a beautiful process, but nobody is going to comply with the process if they cannot perform it within available budget and resources. So test automation is key. If you want to adhere to the standard, you need test automation. Otherwise, it's not going to be fuzzy. So when we talk about test automation, let's first look at what are the artifacts of testing. What kind of artifacts do we have to deal with when we test? We have to have a set of input data, or test data, usually. What exactly is the form of that data depends on the test objectives and the type of system. But we need a driver, there is a program that takes that data and basically sends events or calls the system under test, following the right sequences of calls and monitoring the behavior of the system. Then often we have stubs. Very often the system under test cannot be executed in isolation. It needs to interact with something which may not be available, or which may not have been tested already, or which may not be used at the time of testing. In embedded system, those stubs may emulate the environment of the hardware. In service-oriented systems, those stubs may emulate other services. But you need that to execute the system under test. And of course, you need a so-called oracle or verdict mechanism. A mechanism that tells you whether the test case fails or passes. If you don't have that, testing is a bit difficult. And based on that, then, what are the automation needs? What do we need to automate? Well, first, we need to automate test case generation. We are usually dealing with hundreds of thousands of test cases. We need some kind of automated mechanism that tells us whether test case passes or fails. And usually, it cannot just be that someone enters manually unexpected results. In many systems, expected results are not known or cannot be computed with available resources. But I'll get back to that. Tester generation, test driver generation, logging and analysis of test results, and something which is very often forgotten, but which is absolutely crucial, is supporting test suite evolution. As we all know on projects, requirements change. And on some projects, requirements change a great deal and very frequently. So you need to be able to determine what are the impact of those requirements changes. For example, regression testing. And from a purely testing standpoint, what test cases are obsolete? What test cases need to be rerun? What test cases do not need to be rerun during regression testing? So you need support for test suite evolution based, for example, and primarily on requirements changes. And very often in practice, the activities that are actually supported with automation are the ones I've highlighted in blue here. That is, generating a test driver based on a set of test case specifications and the logging and analysis of test results. The rest, in most environments, is not or very weakly supported. Now the question is, what are the consequences of that? There are many consequences that I'm going to go through. First is that test automation is not scalable. Imagine dealing manually with hundreds of thousands of test cases. A requirements change comes in. Which test cases are obsolete? Then by the time you are done, another change comes in. Which test cases are obsolete? Well, the result of that is that people basically define very small and limited test suites, because that's all they can handle. I've seen in a company that I won't name, test suites of 32 test cases. Why? Because that's all they could handle manually, you know? And so this is just not manageable. If you don't have a way to automatically generate and evolve test suites, you just can't do it. It's expensive, because what's more expensive in software development is people. It's not licenses, hardware, it's people. So, you know, everything that is manual is expensive. Then, of course, the possibility is to outsource to, you know, to a country where labor is cheap. But we all know that this comes with challenges as well. But that's what people have been doing. Instead of automating, they have been outsourcing to low-cost countries. And we all know another problem is that independently of cost, competent IT people are difficult to find. In Luxembourg alone, in the next 2 years, the companies will need 600 additional IT specialists. We only train 100 at the university. Okay? So, of course, an alternative is to resort to incompetent people. Many people do that too. You know, though, you know. But it's a wrong problem. As you know, nobody is good at manual, lengthy, repetitive tasks. If you give me a manual, lengthy, repetitive task, and you make me do that all day, I'm going to do a terrible job. I mean, I just don't want to do this. Nobody wants to do this. Especially competent people. And then what happens then also is that testing cannot be systematic, because nobody can systematically go through those grinding tasks of managing large test suites manually. So eventually people stop being systematic. And another problem is that you cannot be systematic because manual testing really leads to resource shortages, and people take shortcuts. And it's not necessarily visible to project managers, but those shortcuts are actually happening. And when you are not systematic, you are not predictable. If you don't systematically apply a test strategy, then what happens is you cannot learn from the past. You cannot say, well, this is what we did in the last 3 projects, and this is the type of results we can expect. No, you don't know, because on every project you took shortcuts and God knows what happened. Very often people actually are not able to tell you how they tested the system. They're only able to tell you that, well, they had 3 people and they worked for 3 weeks. And then you keep asking, yeah, but how did you test the system? Well, we have 3 people who tested for 3 weeks. I mean, this is not a very predictable way of working. So now, in my title, I had another one, models. And I don't know to which extent you are familiar with model engineering, but I'll give you a high-level view on that. The model in software engineering is an abstract analyzable description of software artifacts created for purpose. Model in software engineering can be anything. Something you probably are familiar with are business process models. That's one type of model. But you have many other models. In real-time system, you can have state machines. You can have use cases are a form of models, except that sometimes they are very informal. And there are many international standards to support modeling. You know the UML, of course, but there are many derivatives of the UML, SysML for system engineering, MARTE for real-time embedded systems, BPMN, for business process modeling that describe business processes and services. And models are used for many different purposes. To describe requirements in a precise manner so that all stakeholders agree on the requirements of the system, to describe architectures, to describe the different interfaces, for example, of services, of components, so that different teams and distributed teams can work together and agree on the way their components are going to interact. Behavioral models, for example, in real-time system to determine how concurrent tasks are going to synchronize and exchange data. And of course, what is of concern to us today, test models, that is models that are used to drive test automation. Models that provide enough information so that you can automate test case generation, test oracle generation, or verdict generation, etc. And the idea of a model is that it's a partial representation of the system or the environment that is much more and much simpler, of course, than what you are modeling. That's, and it's analyzable in order to support task automation, for example, test automation. If it's not analyzable, there is nothing you can do in terms of automation. And modeling is used in all engineering disciplines. There isn't an engineering discipline where there is no modeling. Of course, in software, modeling engineering tends to happen more in certain sectors. Automotive, you have heard, for example, of Simulink, which is a modeling language widely used in embedded systems, and in particular in automotive. Aerospace, government, for example, here we have, and I'll show you, the computing center of the government here has a methodology based on modeling, mostly to interact with their contractors and to define clearly what they expect from their contractors and how they are going to validate the system. But I'll tell you about that. But what is important is that it's also a key technology to support testing. And in fact, when you bring modeling and testing together, you get sort of model-based testing, which is a strategy, which is the topic of my talk today, to automate testing. But how you do it is very driven by the application domain. So what is the general process of model-based testing? Usually people have a mental model of what the system should do, but it's not explicit. So the idea of model-based testing is that you make that mental model explicit, and you actually, using a specific notation, using a specific methodology, model either the system or the environment of the system in a form that is analyzable. It can be a business process model in the BPMN notation, plus other things. And then from that, you have automated tools to derive test suites and test scripts, test stubs if needed, and test oracles. And also, that model is used to actually define test objectives. You know that in that business process model, you want to execute a set of scenarios, and those are your test objectives. And they are explicit, and they are known. And they can be discussed. Eventually, of course, you get test results that you analyze, and you may find out that some failures are due to a mistake in the model, not a mistake in the system. So then you update the model, and it's not a problem. You have learned something, and something we should remember is that software systems usually have a lifespan of 15, 20, sometimes 25 years. And those models are artifacts that you are going to evolve, maintain, and use for 15, 20, 25 years. And of course, they are going to evolve, they are going to be refined, they may be corrected from time to time, and it's what should be expected. You may also realize that you need to strengthen your test objectives. If you find that the system is less reliable than expected. And the way, this is of course a general process. The way you're going to implement that is very specific to a particular domain. The way you are going to implement that process in an embedded system on the ECU of a car is not going to be the same way you are going to implement that system, that process on, for example, an e-government system implementing a business process. It's not going to be, you're not going to do that at all the same way. But the general process of model-based testing looks like this. So now I'm going to show you examples of 4 projects we have here in Luxembourg. Well, of course, what I'm going to tell you is based on a much longer and substantial experience over the years, where I have basically devised technologies to implement the MBT process in many domains, ranging from robot controllers to video conference systems, to safety critical systems in the oil and gas industry, or offshore platforms, to the automotive and satellite sector, the legal and financial sector, and etc. And for many different purposes, where testing was focused on safety, robustness, functional testing, performance testing, security testing. There are many different types. People tend to have very different priorities when they do testing, depending on the field and domain. So let me start with the first example. And I'll go through 4 examples, and I'll get back to more general considerations, using those examples to ground my conclusions. So first is an example with Delphi, an automotive supplier, present in Luxembourg, an American company, as you know. And here it's about testing closed-loop controllers. So as you know, in the automotive sector, they develop a lot of software that is eventually deployed on electrical control units. Those things that control your car. They control the braking system, the injection system, the cruise control system. Now more and more, cars have radar systems with automated braking mechanisms where the car is controlling its environment and is identifying potential obstacles, etc., etc. And that software is increasingly larger and more complex for many reasons that I mentioned on this slide. So software development is becoming really, and it has been for a long time, a challenge in the automotive industry. What are closed controllers or dynamic continuous controllers? They are pieces of software that control devices. Control devices whose position is to be controlled, speed is to be controlled. And so basically, increasingly everywhere, we have those dynamic controllers that control devices, valves, engines, robots. And this is very complex software, usually which is specified by partial differential equations. It's software that has continuous behavior. But there is more and more of it. So how does it develop software and how does it develop that type of control software in the automotive industry? Usually they follow three large phases. Of course, this is a simplification. They have model in the loop, software in the loop, and hardware in the loop. Here, everything is a model. The controller is a model. The controller is the model, the environment of the controller is the model, and usually what they do is that they use technologies like Simulink, which is a proprietary technology for modeling, more particularly control software, but not only. And they need to model the environment because they need stubs, as I told you before. They need to model what the software under test, the controller, is interacting with. Otherwise, they cannot execute it. Yeah, they cannot test it. Then, eventually, they move up to the point where, with hardware in the loop, they have the actual code, compiled code running, and the actual hardware. Hardware or physical simulation. They have those racks. And they have the actual software and the actual ECU. But of course, the problem is that here, when they do testing, testing is very expensive. They can only run a few test cases. You cannot run many test cases. You have the actual hardware, the actual ECU. So, you're not going to run thousands of test cases. So the question is, which ones? Which test cases do you run? Moreover, you have no guarantee that the behavior of the software here is the same as here. The model is not an accurate, faithful representation of reality. Not always. So, but the idea I'm going to tell you is that we are going to do testing here and here. And what we're going to do here, because here we can afford to run a lot of test cases because we're only running models. So we can run as many test cases as possible given computational resources. We can run test cases overnight without human intervention. It's just, here running a test case means simulating a Simulink model. That's what it means. So what we're going to do here is that we are going to search for worst case scenarios in the space of possible inputs and configuration parameters. And those worst case scenarios are going to become the test cases that we run here. Because of course, if you have to choose test cases here to run, ideally you'd like to run the worst case scenarios, and the idea is that if you are okay with the worst case scenarios, you are probably okay in general. Of course, there is no proof, but it's a way to gain confidence, I guess. So, we are here, I'm going to tell you what we do is testing during model in the loop testing. So this is the goal of model in the loop testing, is to ensure that individual functions behave correctly entirely on any hardware configuration. And this is important, on any hardware configuration. So, what is a controller? What a controller does is that it controls a device, and during meal, the controller is the model, and that's what you're testing, actually, you're testing the controller. And the environment is So what we did, we came up with a solution where we have a methodology basically where they define their requirement as structured restricted natural language in the form of use cases, but following a very particular methodology which makes the use cases analyzable. Why use cases? Because this is what they call requirements, this is how they work. That's their current practice. But they used to have very informal use cases, not following a particular methodology. We devised a very precise methodology for them to be able to keep writing use cases, but in a way which, in a form which is analyzable and enable the generation of traceability links and the generation of test cases. At least black box test cases. Okay? And that's what we do. And here, what's interesting is that traceability is a byproduct. Traceability comes for free. You keep traceability links as you are generating test cases. So then, when comes a change, you have the traceability links. They are not manually generated. They are part of the test generation process. Okay? So, they have, this is an example of a system that is very simple. It's a system that sends car seat occupancy. And the main complexity of that system is when hardware breaks down, when a sensor stops working. So that's where most of the complexity of the system is dealing with hardware failure. And so that system interacts with a lot of sensors and electronics and stuff like that. And each use case is described by use case specification, which follows a very specific template and which are written using restricted natural language, following very precise rules, so that it's analyzable. And here, the model-based testing steps are very specific. You know, I showed you the general model-based testing process, but here it's how it's implemented in a particular example. We have restricted use case model specification, we have a domain model, we have some constraints that tells us what can be done when, in a somewhat precise manner. And for example, the domain model defines what type of errors can happen in the system, sensor errors, other kind of errors, what kind of diagnosis the system can do, what kind of devices the system is interacting with. That's what that part of the model is doing. So when I told you the model in that case was restricted use case models, it's not true. There are additional pieces as well. Okay? But we try to minimize it. And then what we do is that we generate an intermediate test model that facilitates test generation and eventually generate test scenarios, or what we call abstract test cases, and eventually test scripts, or what we call concrete test cases, in the particular target test script language that they are using in their context. And the last example is with a satellite company, and here it's about automated testing of data acquisition systems. Data acquisition systems are systems that get very structured and complex data transmitted by satellites and extract information from those files, very large files, and log files saying, for example, what happened during the processing of those files, what errors they found. If they found, for example, commonly they find transmission errors that they have to fix. Okay? And this is based on a particular configuration that describes how data is being transmitted, what protocol is being used. And those systems are very complex because they are basically processing extremely structured and complex files, and very large files. So you imagine what a test case is here. A test case is a very large input transmitted file. Great. So you're going to do thousands of that manually? I don't think so, you know. So of course, you know, testing is limited if it's manual in such a context. So what we did, without getting into detail, we actually modeled, for those who know, we modeled using class diagrams, or specific types of class diagrams, the structure and content of the input transmission files, the structure and content of the output log files, and also the configuration file, it doesn't matter. So we describe very precisely the structure and content of all the files involved, and we describe constraints between those files. If certain conditions are true in the input, certain conditions must be true in the output. So we model that under the form of constraints. And we use that to automate testing. And the general testing approach is that we have an input generator that basically generates a large number of input transmission files that contain errors, or typical errors that you have in those files transmitted by satellites. And we automatically analyze the log and data file in order to check that the constraints are complied with. If not, it's a failure. So this is our oracle, our test verdict. Okay? So now I give you, for example, now so what? So what? You have some examples. There are many questions that we can answer that I have answered based on those experiences and the many experiences I've had before. What kind of models do we need to build? Well, as you have seen, there is quite a variety. Simulink models, business process models, class diagramming constraints, use case specification and domain models. And you have seen the 4 projects were completely different. Why? Because the domain is very different, the type of system is very different, the test objectives are very different, the targeted faults, the oracle mechanism you can use to detect a failure, also the modeling skills and existing practice in the company. At Delphi, they use Simulink. I'm not going to come and say, stop using Simulink. In CTIE, the Government Computing Center, they use business process models. I'm not going to come and say, stop doing that. No, you try to adjust what the practice is to some extent. Yeah. And there are many standards to support modeling. UML, SysML, MARTE, BPMN, and they are adequate in different contexts. For real-time embedded systems, you probably need to use MARTE. For system engineering, where you have both software and hardware, you need to use some SysML. For services and business software, BPMN is probably an essential component. So, then you need to answer that question in context. And that question, you need to answer 2 questions actually. What notation you're going to use? BPMN, SysML, this is just a notation. And something people forget, what modeling methodology you're going to use. A notation is just a notation. You never use an entire notation. You always use a subset. And you always use it in a specific way, at a specific level of detail.
5 minutes now.
Okay. All right, I'm almost done. Okay? How expensive is modeling? Well, from a few days to a few weeks, it depends on context. But what's important to remember is that those models are artifacts you're going to keep for a long, long time. Okay? Because again, the lifetime of a system is 15, 20 years. And you're going to do test automation for 15, 20 years and evolve the models as the requirements are evolving. Okay? But that's not the real question anyway. The real question is, does the cost of modeling overcome the cost of the savings of test automation? This is a real business question. Okay? Everything costs something. So that's not the real question. What kind of technologies do you need? Well, under the hood, you need a lot of technologies, but the user doesn't need to see them. You need to rely, depending on the problem, constraint solvers, mathematical optimization, meta-heuristic search, and genetic algorithms. But this is hidden under the hood. That's a technical difficulty that the user doesn't get to see. That's the kind of stuff I work on. Okay? And actually, there are several mature model-based testing tools. There are now commercial tools that have reached a certain level of maturity. And which one to use? Here are 3 of the leading tools. Which one to use? Again, depend on the domain, because those tools do different things, they don't do the same thing. They target different domains, some target information system, others embedded systems. They use different modeling notations that may or may not be suited in a given environment. They implement different test strategies, they provide different support, which means that if you want to choose a tool, you have to go through an investigation process and think very carefully about it. And actually, none of the tools may suit your needs. Okay? In that case, you have to use modeling environment to build your own technology. Or you have to augment those tools with additional layers of technologies. Okay? Is it cost effective? Again, I cannot give you a number. I can tell you what are the factors that affect cost effectiveness. So what are the costs? The cost is the cost of modeling, training, and tools, and the cost of actually modeling a system. And the benefits are brought by test automation, the regional test suites when there are changes, having more systematic test process, more confidence, and automated traceability, which helps with regression testing and impact analysis. So the cost benefits vary according to those factors. But my experience is that in most environments, the benefits or how to weigh the costs. Now there are a number of frequently asked questions. What if the model is incomplete or incorrect? Don't forget the focus of model-based testing is not proof, it's automation. If the model is incorrect, you correct the model. We have done something. What's very funny in those projects is that often, before we even get to software test automation, people benefit from the activity. Why? Because in the exercise of modeling, they often realize that they don't agree, which is something they had never realized before. It happens all the time. Okay? Because they are forced to be precise, they are forced to communicate in precise terms by doing modeling. Does anything give me a proven test strategy? No, there is no proven test strategy. You have to do process improvement. It also applies to testing. You have to learn what works in your environment. But it enables you to define and automate a test strategy and then investigate whether it's effective or not. There is no such thing as a universal test strategy that works everywhere for everything. That doesn't exist. Can I just buy and apply some more commercial ABT tools? Sometimes yes, often not, because they don't match exactly your needs. So you have to investigate, and if you buy one, you have to tailor it to your needs. Isn't MBT too expensive to introduce and tailor to our needs? Question I get often. Well, everything costs something, but manual testing is much more expensive, except that it's often hidden in the overall cost of the project. And moreover, if you want to return talented developers, you'd better ask them to automate testing than writing manual test cases. Otherwise, they're not going to stick around for a long time. So, because actually, automating testing is an interesting intellectual challenge. People like to do that. It's very interesting. As I told you, you have to resort to, constraint solving, artificial intelligence. So if you're smart people, they will enjoy doing that. Yeah. So conclusions. There are standards for testing, a lot of terms, a lot of techniques in test books. There is a lot of hype. If you read the test tools web pages, they do everything. They solve all the problems I mentioned. But in practice, the hard problems are still open issues in most organizations. That is, the hard problem is, how do you automatically generate test cases? How do you automatically manage traceability? How do you automatically generate mechanisms to detect failures, the oracle problem, the verdict problem? In most organizations, those problems are actually not solved. So there is a lot of hype, but it's only hype. And my argument is that MPT, in most cases, not all cases, in most cases, is basically the only alternative to achieve full test automation, scalable automation. I don't see what else you could do. Honestly, I don't know what the alternative is, in most cases. So the question is not whether to adopt model-based testing, is how. That's a real question. And to do that, because that technology, though much more mature than 5 years ago, is still not a technology as mature as electronics or mechanical engineering. In a given context, there is always a certain degree of investigation and innovation that is required to make it work. And that's why you need applied research and innovation to actually make it happen often. And that's what we do on our projects, as you have seen with Delphi, AI, and others. So, thank you very much, and have a good day.
Do you have any questions to Lionel? Questions? Yeah? Kevin?
Kevin Ryan from Lero. And I think it was a really excellent talk, so thank you very much. I think you understated one thing, which is you didn't mention that the approach you're taking has the potential to do better testing. You're only talking about the fact that it saves money in automating what people currently do. But what people currently do is not good enough. And what you're saying, that it has the potential, when you talk about the cost, it has the potential of saving on the massive cost of failures.
Well, what I said is that testing is going to be more systematic and more predictable.
Yeah.
Of course, more systematic testing means better software.
Yeah.
Of course. Because if you are not effective, cost effective, you are going to have to take shortcuts. So obviously this is going to have an impact on the reliability, safety, security of your system. Yes.
there another further question? Then maybe I have a funny question.
I like funny questions.
Yeah, because I met you when you were an expert in software measurement, and when we use systems like this in the automotive area at the moment, or be it also in the medical area, we have to prove 100% coverage. Yeah? So we also deal with the term traceability, and I think your approach is exactly that has to be followed by industry. But what we are forced to is a kind of measurement of how we achieve the 100%.
1% of what?
Yeah, of the testing. So when we play the
No,
test
but of
case,
what? Coverage has to be defined.
Yeah, coverage has to be defined. That's right. You only have requirements
Yes.
coverage, but there is other types of coverage. Yeah?
And even requirements coverage can be defined many different ways.
Yeah, you see. Now we are back at this old time. Okay, this is the discussion we had 17 years ago. But you were good in measurement. So do your systems also provide some kind of matrix when they create the reports? How do they look like?
Well, when it's automated, it's not very difficult to provide data because it's automated. So
Yeah. The difference.
Yes.
Okay.
I would say that measurement is not really a challenge when all testing is automated. Because you can collect all the data you need to provide the measurement people want.
Yeah, okay.
But the main challenge is to define what, for example, requirements coverage means for a certain type of system in a given environment.
Yeah.
And this is where, for example, in the case of IE, what does requirement mean? The IE project with, that specific methodology for use case.
Yeah.
What that means is you cover certain aspects or certain scenarios in the use cases. But again, what does that mean in practice?
Yeah.
Because you know how use cases work. You have the basic flow of events and you have alternative flows of events. And those alternative flow of events can branch off different steps of the basic flow of events.
Yeah.
So you have all kind, and then you take into account data. Because use cases are executed by taking input data. What kind of data? It's what coverage means.
I agree with you. I'm not you can measure zero C1 coverage, branch coverage. But also requirements coverage, I agree, you can have different levels of requirements, as you mentioned. Yeah? Custom requirements, system requirements, software requirements, it's a different
another challenge of coverage
yeah.
is that usually there are certain parts for example, of the specification, like certain scenarios in the use case,
yeah.
or certain parts of the source code that usually are not executable.
Yeah.
So that means you never actually reach 100%. So let's say you reach 80%. The question is the remaining 20% feasible?
If it's easy,
and that question is undecidable. It's
Yeah.
undecidable. You cannot automatically answer that question.
Okay.
So then this is also another challenge when
Yeah.
you talk about coverage.
Okay, yeah, good. So it seems there's one thing more, because when you have an automation, you get one result. What we are required by the industry is we have to have a trend. So they want to see that how we come to an increased coverage of the.
Yeah.
So it's still more than just running the test, but you must have a kind of software measurement plotting chart mechanism in the background, like a dashboard.
Yes, yes.
Yeah.
And but this can be easily produced when testing is automated.
Very easily displayed.
Yes.
Yeah. Okay. So Mikko says, he's arguing like me 70 years ago, so that's the reason why we could work together. Yes. Okay. So thank you very much, Lionel. Yeah. We are late, of course, 10 minutes late, and also we have to rearrange the room here. Yeah? And I've seen that we did not change that in the local program. So to leave the people time that we can change the room, make a small shift that we do the coffee break now, yeah? Right? And then we